We will discuss the meaning and concept of the definite integral, focusing specifically on how it differs from the Riemann integral. Consider a non-negative continuous function f defined on a closed interval from a to b. The area of the region bounded by this non-negative function f and the x-axis can be calculated using the Riemann integral shown on the screen. The formal definition of the Riemann integral must be established through the concepts of the infimum, greatest lower bound, and supremum, least upper bound. So we will save that for later discussion. For now, it is enough to understand that the Riemann integral can be used to interpret area. Our purpose here is to distinguish between the Riemann integral and the definite integral. This screen explains the concept of antiderivatives. Suppose that f is a continuous function defined on a closed interval from a to b, where f does not need to be non-negative. If we say that another function f is an antiderivative of f, it means that f is continuous on the closed interval from a to b, and the derivative of f at point x, denoted as f prime of x, equals f of x for every x in the open interval from a to b. This is shown in the last line on the screen. This screen introduces a crucial theorem, the fundamental theorem of calculus. It mainly builds the connection between antiderivatives and the Riemann integral. Let f be a continuous function defined on a closed interval from a to b, and assume it has an antiderivative f. Then, the Riemann integral of f on the closed interval from a to b is equal to f of b minus f of a. This is shown in the very last line on the screen. In short, Riemann integrals can be computed through antiderivatives. This screen explains that it is not true that every function has an antiderivative. Let's look at the function sign of x over x, or the function e to the power of x squared, which are displayed in the second line. These two functions have no antiderivatives, meaning we cannot find a function f where f prime of x equals these functions. In technical terms, their indefinite integrals do not exist. Because of this, we are unable to use the fundamental theorem of calculus to calculate their Riemann integrals. To put it another way, the two integrals in the very last line cannot be solved by the fundamental theorem of calculus. Since we cannot use the fundamental theorem of calculus to calculate these two Riemann integrals, this means that they shouldn't be treated as definite integrals. They can only be considered Riemann integrals. Later on, we will discuss that if a function f is continuous on the closed interval from a to b, then f is guaranteed to be Riemann integrable on that interval. In other words, its Riemann integral exists. Even though we haven't strictly defined Riemann integrability yet, as explained earlier, if a function f is non-negative and continuous on the closed interval from a to b, it means that its Riemann integral on the closed interval ab is simply the area between the function f and the x-axis. So, if we can find a closed interval ab such that the function sign of x over x and the function e to the x squared are non-negative, then the integrals displayed in the very last line represent the area of the region bounded by the x-axis. That is to say, these two integrals are indeed Riemann integrals. To see why these two integrals are not definite integrals, we need to clarify the difference between definite and indefinite integrals. The expression in the second line is called an indefinite integral. Notice that it does not have a lower limit of integration and an upper limit b of integration, but it does have a constant c. Here, function f is the antiderivative of function f. Keep in mind that a strict definition of an antiderivative must consider continuity on a closed interval from a to b, as we established earlier. Even though this indefinite integral does not explicitly look at continuity on the closed interval ab, we can still treat f as the antiderivative of f.
Why?
Because we only need to assume that the derivative of f is f. meaning we are implicitly assuming that we are working with continuous functions. Once you understand this, the concept of a definite integral becomes straightforward. As you can see in the second to last line, it is just like an indefinite integral, but with the lower and upper limits a and b added. To calculate it, you simply plug the limits a and b into the antiderivative f. Our phrase for this is the value of the antiderivative at the upper limit minus the value at the lower limit. So, a definite integral can only exist and be written as shown in that line if the function actually has an antiderivative. Since the two functions we discussed before, sine of x over x and e to the x squared, do not have antiderivatives, they simply do not have definite integrals. This screen shows that if a function f is continuous on a closed interval from a to b, then by the fundamental theorem of calculus, the definite integral and the Riemann integral of this function f are exactly the same. In addition, its value is simply the antiderivative at the upper limit b minus the antiderivative at the lower limit a, which is f of b minus f of a. From a certain perspective, the Riemann integral seems to be more general than the definite integral. Evaluating an indefinite integral is essentially just looking for the antiderivative. Without the backing of the fundamental theorem of calculus, calculating indefinite integrals would seem almost meaningless. After all, finding an antiderivative is just doing the reverse operation of a derivative. From an application standpoint, performing a reverse operation on its own does not really serve much purpose. The expression displayed in the second line is a Riemann integral rather than a definite integral. Because we cannot find its antiderivative, meaning we cannot do the reverse operation, the fundamental theorem of calculus is off the table. This means all those integration techniques for indefinite integral we spent so much time learning are completely useless in this case. But remember, these two are Riemann integrals, so they definitely have an area. It is just that we cannot use the fundamental theorem of calculus to find it. So, how do we calculate it? This is where the magic of math comes in. We can actually use numerical integration to find an approximate value. Strictly speaking, we can never know the exact value of these two areas or the exact value of these two Riemann integrals. But the approximations we get from numerical integration can get incredibly close to the exact value. To put it another way, no matter how small an error you want, you can always calculate an approximation that meets that requirement. Of course, this means we have to write computer programs and let computers handle the heavy lifting to find these approximate values. There are many ways to do numerical integration, and one of the most popular is Simpson's rule. The basic idea is simple. We can slice the function curve into very thin pieces and approximate each piece with a parabola. The finer we slice the curve, the more accurate the parabolic approximation becomes for each segment. This means we only have to calculate the definite integrals of these parabolic functions. Once we add up the definite integrals of all these tiny parabolas, we get our approximate integral value. Because a parabola is just a quadratic function, its definite integral is easy to calculate, and that also makes it easy to estimate the error. So, in a broader sense, even if we did not learn all those tricks for calculating indefinite integrals, in other words, if we do not know how to find the antiderivative or simply cannot do it, we can still use numerical integration to get an approximate answer. From an application standpoint, there is really no need to spend so much time and energy mastering so many indefinite integration techniques. Most highly complex functions are incredibly hard to integrate anyway. Sometimes their antiderivatives do not even exist, yet we waste a lot of effort trying to calculate them. Ultimately, what we actually deal with in real-world applications are Riemann integrals or definite integrals, not indefinite integrals. In this example, we're going to compute the definite integral of the sine function from the lower limit of 0 to the upper limit of pi over 2. Because the antiderivative of sine is negative cosine, we plug the upper limit pi over 2 into cosine function, and then subtract the result of plugging the lower limit 0 into cosine function. This gives us an integral value of 1. This value of 1 is also the area of the region formed between the sine curve and the x-axis from 0 to pi over 2. This theorem shows that a Riemann integral over the closed interval from a to b can be broken down into the Riemann integral from a to c plus the Riemann integral from c to b. Here, the point C can be any point lying between A and B. Intuitively, if we assume the function f is non-negative, the area bounded by f and the x-axis from A to B simply equals the area from A to C plus the area from C to B. But keep in mind, we do not actually need to assume the function is non-negative for this theorem to work. Even though we are focusing on Riemann integrals here, the same rule applies to definite integrals. This theorem shows that Riemann integrals have a linear property. Just as displayed on the screen, the integral of functions added together equals the sum of each individual integral. This also applies to constant multiples of a function, meaning we can pull the multiplier outside of the integral sign. When we multiply several functions by different constants and add them up, we call it a linear combination. This term actually comes from linear algebra. We will have a chance to discuss linear algebra courses later on, so for now, you can just ignore the concept of linear combinations. In this example, we're going to evaluate the integral of a polynomial function. Using the theorem from before, we can break it down into multiple simple integrals, just like the first equation you see on the screen. After that, the rest of the integration is quite easy to follow. In this example, we are going to evaluate the integral of a function made up of trigonometric functions. First of all, the first equation is just multiplying the secant of x through. For the second equation, we use the theorem from earlier to break the integral into two terms. In the third equation, we find the antiderivatives. And in the very last equation, we plug the upper and lower limits into the antiderivative. After simplifying, we get the final value of the integral.